This is Physics 2212, Lab 2, Lines of Charge. Introduction. The purpose of this lab is to produce a more precise computational model using glow script of two charged tapes exerting electric force on each other such that one tape floats a small distance. This is based off of Lab 1. And the results from last one is that we found that the charge on the tape was 9.9373 times 10 to the negative 9th. And then we computed through trial and error that the new charge on the tape was 9.9373 times 10 to the negative 9 times 2.2286, so that the electric force was equal to the gravitational force. And in this experiment, we assumed that air resistance was negligible, each U-tape had the same charge, and the charge was evenly distributed across the tape. And also in this experiment, the system was the charged U-tapes, the surrounding was Earth. And then just as a quick recap, we created two U-tapes, hung one by its ends on two textbooks, then approached it, or just two objects, and then approached it with another charged tape, and then measured the distance of repulsion. And then some fundamental principles. We used Newton's second law, that the net force is equal to mass times acceleration. Coulomb's law was that the electric field is equal to kq r hat divided by r squared, and that the electric force can be on a charge or a collection of charges is that charge times an external electric field. And then we use superposition to find the net electric field of multiple charges just by adding up the total charges on the tape. And then some physical constants from Lab 1. We have our K constant, the charge of an electron and a proton, the atom length, the acceleration of gravity on Earth, and then what we had to multiply by for our charge from Lab 1 to be the new charge. And then we have the tape width, length, the meters, and then the distance that was separated. And then we estimated the new net charge on the tape. Yes. And then the code below creates a line of charges for our computational model. Next, we have a nested for loop, which divides the tape model into finite pieces, and then it calculates the electric field and electric force on each portion. It then calculates the total electric field on the tape, which then creates a new arrow for our new model. And then after that, the last lines of code output the model of the net electric force and the net gravitational force on the tapes, which, when we calculate it, it should be the same. And then here is the final model with the white arrow representing the electric force, the red and the blue representing the line of charges on the tape, and then the purple representing the gravitational force. And as assumed, the magnitude of the electric force and the gravitational field, and the gravitational force is the same at 1.961 times 10 to the negative third. And then just some possible errors that could occur in this experiment was that tape A and tape B don't have the same charge. The charges could have been transferred to other objects in the surroundings during handling. And in the model, the air resistance was neglected. However, in real life, this cannot be assumed. And then here are some what-if questions. What if you had modeled each of your tapes as a single point charge, like in the previous lab? Compare the estimated value of the charge you get when you use the experimental data to produce a point charge model to the value you got with your line charge model. And then, like we said in the beginning, the point charge model, you have 9.9373 times 10 to the negative 9th. And then in the line charge model, you have a new Q that is 2.214 times 10 e to the negative 8th. And then, why do the estimates differ? Which value is more likely to be closer to the real value and why? So I said that these values differ because their models use different levels of precision. The line charge model is more likely to be closer to the real value because it uses smaller portions of the tape to calculate the net electric field and force. Overall, it more accurately represents the real life situation than the point charge model. And that's it. Thank you.